Welcome to episode 18. In this episode, we'll add support for a Commodore 16 keyboard to the 6809 system. We'll start by outlining the requirements and design goals for the keyboard controller. Next, we'll go over how matrix keyboards work and how we can detect key presses and releases. We'll briefly discuss 8051 microcontrollers, since we'll be using an 8051 family microcontroller to scan the keyboard matrix. We'll cover a detailed hardware design, and finally we'll implement and test the keyboard controller and add software support to the monitor program so we can use the keyboard as an input device. Let's get started. Right, Dave from the future here. The video got to be kind of long, so we'll do the software support in the monitor in the next video. Our requirements and design goals for keyboard support are as follows. The main requirement is to allow the 6809 system to read keyboard input from a directly connected keyboard. Since the goal of the project is to create the equivalent of a 1980s home computer, a keyboard is an essential component. The specific keyboard we'll be using is the Commodore 16 keyboard. The Commodore 16 was one of Commodore's last 8-bit systems, and there are a fair number of Commodore 16 keyboards available on the surplus market at reasonable prices. The second requirement is to use a microcontroller to handle the task of scanning the keyboard matrix to detect key presses and releases, and to use a FIFO device to communicate the key press and release events to the system. Many 8-bit computers required the host CPU to do the scanning for key presses and releases, which increases software complexity and takes time away from the main program. In our design, the 6809 system will be able to read the scan codes by simply reading from the memory location where the FIFO memory device is mapped. One of the overall goals for the 6809 system is to use authentic parts, meaning ones that would have been available in the 1980s. This goal motivates our choice to use an 8051 family microcontroller as the heart of the keyboard controller. Specifically, our goal for the production version of the system is to use an 87C51 microcontroller. However, since these are obsolete and somewhat hard to obtain, we'll do the firmware development for the keyboard controller using an Atmel 89C51, which is widely available and easily obtained. Next, let's talk about how keyboards work and how key presses and releases can be detected by a digital device such as a microcontroller. Fundamentally, a keyboard is just a bunch of push-button switches. When a key is pressed, it creates an electrical connection between two switch contacts. A typical way that a microcontroller or other digital device can detect whether the switch is pressed is to connect a digital input to one switch contact and use a pull-up resistor to establish a default logic level at the input when the switch is not pressed. This means that the input will read a value of 1 when the switch is not pressed. The other switch contact is then connected to ground. When the switch is pressed, a low impedance path to ground is created, and the digital input will see a low voltage and thus read a 0. This is a very straightforward arrangement and allows the key state to be easily determined. However, this approach does not scale very well since each switch will require a separate digital input. Since a typical keyboard will have a fairly large number of keys, too many digital input pins will be required to make this scheme practical. To reduce the number of digital I/O pins required to detect key presses and releases, most keypads and keyboards use a switch matrix. A switch matrix consists of rows and columns. Each row and column is electrically connected along its length and is a single node in the circuit. The key switches are placed at the intersection of a row and column. When the switch is not pressed, there is no connection between the row and the column. When the switch is pressed, the row and the column are connected. Detecting which keys are pressed requires one digital output per column and one digital input per row. The row inputs have pull-up resistors and are thus normally at a high logic level. Let's say we want to know which keys in the middle column are being pressed. The output for the middle column, Q1, is driven to a low voltage. The other outputs, Q0 and Q2, are not driven and will be in a high impedance state. Depending on which of the keys in the column are pressed, the inputs I0, I1, and I2 will be driven to a low voltage. For example, if the top key is pressed, then I0 is connected to the low voltage generated by Q1 and will read a 0 rather than a 1. This means that we know that the top key in the middle column is pressed. Similarly, if the middle button is pressed, I1 will read a 0, and if the bottom button is pressed, then I2 will read a 0. In order to determine which keys are pressed and released, the columns are driven to a low voltage one at a time, and the inputs are read. This process is called scanning. One consideration when designing hardware to scan a keyboard matrix is that if multiple keys are pressed, outputs can be connected to each other. For example, if two keys in the same row are pressed at the same time, then the outputs for those columns are connected. If both outputs are being actively driven, especially if they are generating different voltages, then current can flow from one output to the other. This is why the outputs for the columns that aren't being actively scanned should not be actively driven. Overall, the advantage of matrix-encoded keyboards is that they allow a large number of keys to be supported using a relatively small number of digital I/O lines. Specifically, the number of keys that can be supported is the product of the number of rows and the number of columns, with each column requiring one output and each row requiring one input. The Commodore 16 keyboard uses an 8x8 matrix, so we will need 8 digital outputs and 8 digital inputs. The main disadvantage of matrix-encoded keyboards is that detecting key presses and releases is more complicated. However, we will see that a microcontroller will make this task fairly easy. At the heart of the keyboard controller, we will use an 8051 family microcontroller. The 8051 series was introduced by Intel in 1980 and was a successor to its popular 8048 microcontroller series. A microcontroller is basically an all-in-one computer system on a single chip with ROM, RAM, and useful peripheral devices such as digital I/O ports, timers, and UARTs built in. They are widely used for embedded control applications, and serving as an intelligent keyboard controller is a typical application. The 8051 series saw widespread adoption and is still being used today. Although Intel is no longer making microcontrollers, numerous vendors continue to offer 8051-compatible microcontrollers in a wide variety of configurations. One interesting feature of the 8051 family is that there is generally extensive binary code compatibility between different 8051 family parts. So the same code can be used, for instance, on a genuine Intel 8051 and on an Atmel 89C51. The original 8051 had 4K of program memory, 128 bytes of RAM, 2 timers, a UART for serial communication, and, most importantly, 32 digital I/O pins. We will need a total of 26 digital I/O pins for the keyboard controller, so the 8051 has more than adequate I/O for our needs. In order to deploy firmware for the keyboard controller, we need to be able to load our own programs onto the microcontroller. This is not feasible with an actual 8051 device where the program memory is mask ROM, which must be programmed at the factory. Instead, we will use the 87C51 variant of the 8051, which is essentially an 8051 with UV erasable EEPROM as its program memory. Since erasing a UV erasable device is somewhat time-consuming, we'll do the firmware development for the keyboard controller using the Atmel 89C51, which is functionally identical to the 8051 and 87C51, but has flash memory as its code memory, and can be programmed quickly using the MiniPro TL866 programmer. Now that we've covered how matrix keyboards work and described the basic features of 8051 microcontrollers, we're ready to create a test setup. This is the full keyboard controller schematic, but we're only going to be building the part of the circuit that contains the microcontroller and the keyboard connector. This will allow us to verify that the microcontroller is correctly reading the keyboard switch matrix. The 8051 requires a small number of supporting connections and components to run. First, the microcontroller's supply pins should be connected to VCC and ground. Second, the 8051 requires an active high power-on reset pulse. This can be generated by a 100 nanofarad capacitor connected to VCC. In the actual 6809 system, the system reset signal will be used instead. Third, the microcontroller's EA pin should be tied high. This will cause code to be executed from the microcontroller's internal program memory. Finally, a crystal and two 30 picofarad capacitors are needed to generate the clock frequency. We'll use an 11.0592 MHz crystal, which allows the microcontroller to run at a reasonable speed, and can be divided to generate standard UART frequencies, which is useful, as we'll see in a moment. To interface the microcontroller to the keyboard connector, we use port 1 to generate the column outputs, and port 0 to read the row inputs. There are pull-up resistors on port 0 so that the row inputs will read 1 by default. As the columns are scanned, the firmware will drive the active column to ground so that any keys that are pressed in that column will read a 0. Interestingly, the way that the 8051 generates a high output is not by actively driving a high voltage, but instead by creating a path to a weak pull-up resistor. So, we actually don't need to worry about the possibility that pressing multiple keys in the same row will connect two output pins. Because of the pull-up resistors, very little current can flow between output pins in this case. In order to know whether or not the microcontroller is detecting key presses and releases correctly, we'll use the 8051's UART to display messages on a SparkFun serial LCD. All we will need to do is connect the UART's transmit pin to the serial LCD's receive pin. Serial LCDs are very useful for providing diagnostics when developing an embedded system. The way we know how to connect the microcontroller's I/O pins to the pins of the keyboard connector is by using the keyboard matrix diagram in the Commodore 16 service manual. The numbers on the rows and columns indicate the corresponding pins of the keyboard connector. Before we go through the complete keyboard controller design, let's conduct a quick test to verify that the microcontroller can correctly scan the keyboard matrix. We'll be implementing the keyboard controller firmware in the C programming language and compiling it using the open source SDCC compiler. As always, the complete source code and schematics will be linked in the video description. The main function of the test firmware does hardware initialization and then runs the key scanning code. The hardware UART is initialized, allowing serial output to the SparkFun LCD display. All bits of port 0 are set to 1 to allow it to be used as an input port. All of the bits of port 1, which generates the column outputs, are set to 1, which puts them in a high impedance state. We will see that the scanning code will actively drive one column output at a time to ground. Each element of the press array is set to hex FF. The array has 8 elements corresponding to the 8 columns of the keyboard matrix. Each element keeps track of the last value read from port 0 for the column, and thus records which keys were pressed and not pressed during the last scan. Keeping this information allows the keyboard controller to determine when the state of a key changes. The main loop of the program simply calls the KBD scan function in an infinite loop, adding a short delay after each call. The delay can be adjusted in order to change the scanning frequency. The KBD scan function writes a 0 to the bits of port 1 in sequence in order to drive the column outputs to ground. For each column, it calls the check rows function to read the row inputs to determine which keys in the column are pressed. Finally, it sets all of the port 1 bits back to 1. The check rows function gets the previous row input values for the column being scanned, and then reads from port 0, which determines the current row input values. A loop checks each row bit to see whether the value of the bit changed since the last scan. If the bit did change, then depending on its value, we know that a key was either pressed or released, and the send scan code function is called to indicate that a key press or release event has occurred. Finally, the current row input values are recorded. In the test firmware program, the send scan code function simply sends a message to the LCD display to indicate the column, row, and press or release status. In the final version of the firmware, the scan code information will be sent to the FIFO device to allow it to be read by the CPU. Alright, so here we have our test circuit with the 89C51 microcontroller, and this is the connector for the keyboard, and we have port 0 wired to the row inputs and port 1 wired to the column outputs. And as a test, I have several of the keyboard keys, the 1, the Commodore key, the L, the help key, the F key, and the N key, annotated with the column and row that we expect to see based on their position in the switch matrix. Alright, so I'm going to power on the circuit, and essentially what we should see on the serial LCD is the column and row, and then either a 1 if a key is being pressed, or a 0 if a key is being released. So let's see if it works. Okay, so I'm pressing the 1, and basically what I expect to see is 001, and I do, and when I release it, I see 000, so that looks good. So let's press the Commodore key. Okay, so 501, 500, that looks good. The L key, 251 and 250, excellent. The help key, 771 and 770. The F key, 521 and 520, that's good. And the N key, 341 and 340. So this is a good confirmation that the firmware for the microcontroller is correctly detecting key presses and releases. So I think now we are ready to look at the schematic for the full keyboard controller that shows how we interface it with the host 6809 system. To interface the keyboard controller with the 6809 system, we'll use a FIFO memory chip, the IDT7201. Normal static RAM chips are random access, meaning that any memory location can be directly accessed or modified. A FIFO memory supports only first in, first out access, hence the name FIFO. There is no addressing of data values, and data values written to the FIFO will be read in the order in which they are written. Different FIFO memory chips will have different capacities. The IDT7201 can store 512 values. The IDT7201 has two interfaces, one for writing a byte of data to the FIFO and one for reading a byte from the FIFO. As keys are pressed and released, the 8051 microcontroller will create scan codes and write them to the FIFO. Each scan code contains the matrix row and column and whether the event was a press or a release. For example, if the L key was pressed, we encode column 2, row 5, and a 1 to indicate that the key was pressed. The encoded scan codes are sent to the FIFO using port 2, which is connected to the FIFO's D0 through D7 inputs. Pin 6 of port 3 is used to control the FIFO's write input. By sending a low pulse on this pin, the data present on the data inputs is written to the FIFO. Allowing the host 6809 system to read data from the FIFO is fairly straightforward. The FIFO's output pins Q0 through Q7 are connected to the data bus. A 748CT138 3-to-8 decoder chip is used to generate a chip select signal which is asserted when there is a request to read from the FIFO. When the chip select is not asserted, the FIFO's output pins Q0 through Q7 are tri-stated. When the chip select is asserted, the next data value to be read is output. Because the FIFO should not be read unless it actually contains data, it is necessary for the keyboard controller to provide a mechanism for the host CPU to read the FIFO's status. This is accomplished using a 748CT541 buffer chip. Its chip select is also generated by the 748CT138. The buffer outputs the FIFO's empty and full status flags on D0 and D1. So, by reading the FIFO status and checking bit 0, the host CPU can know whether or not the FIFO has any data available. As you may recall, one of the design goals for the 6809 system is to use authentic 1980s vintage parts, so you might be wondering whether the IDT7201 would count as authentic using this criterion. The answer is yes. I happened to find an IDT7201 engineering sample kit on eBay, and the parts I received have 1985 and 1987 date codes. Note, however, that because FIFO memories are fairly specialized devices, they probably would have been absurdly expensive in the 1980s, and thus wouldn't have been used in a home computer. However, they are inexpensive and easy to find now. Now that we're ready to build and test the complete keyboard controller circuit, we need to update the keyboard controller firmware to send scan codes to the FIFO device. This is fairly straightforward. First, we add code to the main function to set pin 6 of port 3 to a high value, which ensures that the FIFO's active low write input is not asserted. Next, we send a low pulse on pin 7 of port 3, which is connected to the FIFO's active low reset input. This clears the FIFO and gets it ready to store scan codes. Note that the P3_6 and P3_7 variables are single-bit memory locations which directly control pin 6 and 7 of port 3. Single-bit memory operations are a very convenient feature of the 8051 microcontroller family and make digital I/O very straightforward. Finally, we modify the send scan code function to write the scan code data to port 2, which feeds the FIFO's data inputs, and then sends a low pulse on pin 6 of port 3, which clocks the scan code value into the FIFO's memory. Alright, so we have the keyboard controller built on the breadboards here. It's connected to the 6809 system, and what we'll now try is loading the test program in the monitor. So let me reset the system here. Alright, and then we'll use the D command, and then it should be kbd test.ihx as the test program, so that's loaded into the monitor. We'll set the monitor address at hex 1000 and then execute. And now what the system should be doing is reading scan codes from the keyboard controller via the FIFO. So basically every time I press a key, we should see two scan codes being printed in the monitor. So here's the 1 key, the A key, the space bar, the F1 key. So this looks very good, and each key press and release will generate two separate scan codes, one for the press event and one for the release event. So this is excellent progress. It does indeed look like the keyboard controller is working. Alright, so as our last little bit of prototyping and testing, I would like to try using an actual 87C51 device as the microcontroller. So here is a Signetics 87C51 device that my friend Don graciously donated. Thank you, Don. I had two Intel 87C51s, neither of which work. So this is almost certainly a good one. I've verified that it is blank, and it consistently reads data, so I think it's a good part. Let's try to program it and see what happens. All right, so I've got the 87C51 programmed. It programmed and verified just fine. I don't know if it works yet. I am testing it literally for the first time here. So, all right, let's download our test program again and see what happens. kbtest.ihx. Okay, set the monitor address to hex 1000 and execute. All right, and let me press some keys. Oh my gosh, it works. That is so cool. This is our keyboard controller firmware working on a 30-plus-year-old programmable microcontroller. That is super cool. So I declare this project a success. All right, that wraps things up for this video. What we'll be doing next is we need to properly support the keyboard and the monitor program so that it can be used as a first-class input device. I would like to be able to actually type monitor commands on the hardware keyboard rather than on my PC terminal program and have the monitor program respond. I think probably what will happen next in terms of system development is adding support for sound and graphics to the 6809 system, and at that point it'll really be a proper home computer. Okay, I will see you in the next video.